There used to be a logic to the year. Spring came, and you knew it because the dogwoods bloomed and the temperature climbed and the mud dried up and the birds came back. Summer settled in, heavy and reliable, and the nights were warm and the thunderstorms rolled in predictably from the southwest every afternoon. Fall arrived with a specific kind of light, a lower angle, a golden quality, the smell of leaves turning. And then winter locked everything down. Ice on the puddles in the morning, the furnace clicking on, a stillness. Farmers knew this logic. Gardeners knew it. People who spent time outside knew it in their bones. The calendar and the weather were not in perfect agreement. That was never true. But they were in rough alignment. The seasons had a character, a rhythm, a predictable arc that made it possible to plan a life around them. That alignment is breaking down, not in a subtle way that only shows up in datasets and scientific papers, in a way that people across the United States are noticing, describing, and increasingly struggling to make sense of. February hitting 70 degrees in Minnesota. March snowstorms slamming states that haven't seen serious snow in years. October temperatures that used to belong to August. Winters that never really arrive, followed by springs that never really stabilize. Summers that stretch past the point where anything can thrive in the heat. This is not normal variation. Normal variation has always existed. Every region has its folklore about unpredictable weather, its proverbs about not trusting the groundhog, its stories of the weird October blizzard or the January thaw. The difference is that what is happening now is not variation around a stable average. The average is moving. The envelope of what's possible is widening. And the rhythm, the basic seasonal rhythm that shaped American agriculture, American architecture, American ecosystems, and American culture, is coming apart at the seams. This video is about what is actually happening to the seasons in the United States, why it is happening, and what the consequences are. Not in abstract global terms, but in specific, concrete, measurable terms. The phenology, the timing of natural events like flowering, migration, and leaf color that has been recorded for decades, and that is now shifting faster than at any point in the instrumental record. The agricultural systems that were designed for seasons that are no longer reliable. The ecosystems that were built on seasonal timing, cues that are now out of sync with each other. The infrastructure that was engineered for climate conditions that no longer describe the reality. This is the story of what happens when the most fundamental rhythm of life on Earth stops being predictable. And it is happening right now in every state in the country faster than most people understand. Chapter 1: What we mean by seasons, and why the calendar is already lying. When most people think about the seasons, they think about the calendar. March 20th is the first day of spring. June 21st is the first day of summer. The calendar tells you which season you are in, and the weather follows along, more or less. This is a convenient fiction, and it has always been one. The calendar seasons, astronomical seasons, based on the position of the Earth relative to the Sun, marked by the equinoxes and solstices, are about the length of the day, not the temperature. The spring equinox on March 20th marks the moment when day and night are equal in length, not the moment when the temperature becomes spring-like. In most of North America, March 20th is still very much winter by any ecological or agricultural standard. The actual transition from winter to spring conditions, the melting of snow, the thawing of soil, the emergence of vegetation, typically happens weeks to months after the astronomical spring equinox, depending on latitude and local geography. What ecologists and farmers and phenologists, scientists who study the timing of biological events, actually care about is not the astronomical calendar, but the ecological calendar. The ecological calendar is defined by events: the date of the last killing frost in spring, the date of the first hard freeze in autumn, the date when soil temperatures rise above the threshold for seed germination, the date when specific flowers bloom, when specific birds arrive from their wintering grounds, when insects emerge from dormancy. These events define the real boundaries between seasons, and they are far more variable and far more consequential than the astronomical dates. The ecological calendar is defined differently in different places. In the upper Midwest, the seasons might be reckoned by the arrival of the Canada geese in spring and their departure in fall, by the ice-out date on the lakes, by the first thunderstorm of the season and the first hard freeze. In the Southeast, the transitions are subtler. The boundary between seasons is more about humidity and rainfall patterns than about temperature, and the concept of winter is defined by frost frequency rather than snow depth. In the Pacific Northwest, the seasons are defined primarily by the wet season and the dry season, with a relatively narrow window of transition between them. In the Southwest, the seasonal boundaries are defined by the monsoon pattern, the summer influx of moisture from the Gulf of California that transforms the desert landscape, and the two dry seasons that bracket it. All of these ecological calendars are moving. The frost-free growing season in the contiguous United States has lengthened by approximately 2 weeks since 1980, according to NOAA's long-term climate records. The last spring freeze is occurring earlier in the year, and the first fall freeze is occurring later. The soil thaw is happening earlier in spring. The first spring flowers, lilac, forsythia, wild mustard, are blooming earlier than at any time in the recorded history of phenological observation, in some regions by 2 to 3 weeks compared to 50 years ago. This sounds on the surface like a gift: a longer growing season, more time to plant, more time to harvest, warmer winters. What's the problem? The problem is that the ecological calendar is not a set of independent events that can each move forward without affecting the others. It is a network of timing relationships, intricate, evolved over thousands of years, in which one event's timing is keyed to another event's timing, and the whole system functions as an integrated network of biological rhythms. When some parts of that network shift faster than others, the network breaks down. The flowers bloom before the pollinators emerge. The insects emerge before the birds arrive to eat them. The crops are planted before the last frost has passed. The salmon arrive at the spawning grounds before the snowmelt has cooled the rivers to the temperatures they need. The timing relationships that make the ecosystem function are not preserved when the seasons shift, because different parts of the ecosystem shift at different rates, driven by different environmental cues, responding to different aspects of the changing climate. The calendar, in other words, is lying. The month on the page no longer reliably tells you what ecological state you're in. March can be April, November can be September. And the consequences of that confusion for plants, animals, farmers, infrastructure managers, and the ecosystems that all life in America depends on are already visible and are accelerating. Chapter 2. The data. What half a century of records shows. The temperature record for the contiguous United States goes back, in some locations, to the 1850s. The full network of weather stations that provides the climate baseline most commonly used in scientific analysis, the Climate Reference Network and its historical predecessors, has been systematically recording temperature, precipitation, and related variables since at least the early 20th century. That is roughly 120 years of data, enough to establish a reliable baseline and to identify long-term trends. What that data shows, when examined by region, is not a simple uniform warming. It is something more complicated, more geographically variable, and in some ways more alarming than a uniform temperature increase. The continental United States has warmed by an average of approximately 1.8 degrees Fahrenheit, 1.0 degrees Celsius, since 1901, according to the latest National Climate Assessment. But this average conceals enormous regional variation. The northern parts of the country have warmed substantially more than the southern parts. Alaska has warmed by approximately 3 to 4 degrees Fahrenheit since 1925, faster than any other state. The northern Rockies, the northern Plains, and the Great Lakes region have all warmed faster than the void continental average. The Southeast has actually experienced a period of relative cooling in the mid-20th century, sometimes called the warming hole, though it has been catching up to the national trend in recent decades. The warming is also not uniform across seasons. This is the crucial finding that directly supports the observation that the line between seasons is breaking down. Winter has warmed more than any other season in the United States. Winter temperatures in the contiguous U.S. have increased by approximately 3.7 degrees Fahrenheit since 1895, approximately twice the rate of warming in summer. Spring and autumn have also warmed, but more moderately. Summer has warmed the least of the 4 seasons, though its warming is still statistically significant and ecologically consequential. What does it mean for winter to warm faster than summer? It means the contrast between the seasons is decreasing. The thermal difference between July and January, the fundamental temperature swing that defines the seasonal rhythm, is getting smaller. In the coldest parts of the country, this reduction in seasonal contrast is most dramatic. In International Falls, Minnesota, historically one of the coldest cities in the lower 48 states, the January average temperature has risen by approximately 4 degrees Fahrenheit over the past century. The July average has risen by approximately 2 degrees. The seasonal temperature swing is compressing. The precipitation data tells a more complex story. Overall precipitation in the contiguous United States has increased slightly, but the distribution of that precipitation has changed dramatically. The western United States has experienced a significant drying trend, especially in the summer and early autumn, the exact period when plants and ecosystems most need moisture. The eastern United States has generally seen increased precipitation, but an increasing fraction of that precipitation is coming in more intense events, heavy rainstorms rather than moderate, sustained rainfall. which means less of it actually soaks into the soil and more of it runs off. The result is a paradox: more total precipitation, but more frequent drought conditions, because the rainfall is less effective at maintaining soil moisture. Snow cover is a particularly sensitive indicator of seasonal change. The extent and duration of snow cover across the contiguous United States has been declining since the 1970s. The western mountain snowpack, the store of water accumulated in the form of snow over the winter, which melts slowly through spring and early summer and sustains river flows, irrigation systems, and municipal water supplies, has decreased substantially across most of the western mountain ranges. The fraction of winter precipitation falling as snow rather than rain has decreased in many mountain regions. The snowmelt is happening earlier, an average of 2 to 3 weeks earlier in many western river basins than it did 50 years ago. And the peak spring runoff that western water systems are designed around is shifting in timing in ways that the infrastructure was not designed to accommodate. The heat extremes are increasing faster than the mean temperature, a well-documented pattern in climate science that reflects the asymmetric nature of the warming. Hot days are getting hotter faster than cold days are getting warmer, which means the statistical distribution of temperatures is not simply shifting upward uniformly, but is also spreading out, becoming more variable, with more frequent and more extreme heat events, while the extreme cold events are becoming less frequent but not disappearing. This asymmetric change in the distribution of temperatures is directly responsible for many of the paradoxes that people observe. Warmer winters punctuated by occasional severe cold snaps, hotter summers with unprecedented heat events, springs that oscillate between warmth and cold in ways that feel random but are actually part of a systematic pattern of increased variability. The trend in extreme events is arguably more consequential for the functioning of ecosystems and human systems than the trend in mean temperatures. Ecosystems can adapt to gradually shifting means over centuries. They are far less able to adapt to sudden extreme events that puncture the normal range. A heat wave that pushes temperatures 15 degrees above the historical average for 3 consecutive days kills things, plants, animals, people, in ways that a persistent 2-degree warming does not. An ice storm in late April after plants have already leafed out destroys the crops and the ecosystems that were relying on the spring warmth having arrived. The increasing frequency of these extreme outlier events that fall outside the historical range that organisms and infrastructure were designed around, is the mechanism through which the breakdown of seasonal predictability causes actual damage. Chapter 3: Phenology. When the natural calendar stops making sense. Phenology is the study of the timing of biological events. The first bloom of the cherry trees, the arrival of the first robin, the emergence of monarch butterflies from their chrysalises, the day when the first firefly appears. Human beings have been keeping phenological records for centuries, and in the modern era, systematic phenological monitoring has produced datasets that are among the most direct and unambiguous indicators of how the changing climate is affecting the natural world. The USA National Phenology Network, a collaboration of federal agencies, research institutions, and citizen scientists, maintains a comprehensive database of phenological observations from across the United States. The data, which in some cases extends back to the early 20th century, and in others has been systematically collected only since the mid-2000s, tells a consistent story. Spring is arriving earlier, autumn is arriving later, and the biological events that define the ecological calendar are shifting at different rates, creating mismatches in timing that ecological systems were not evolved to handle. Consider the lilac. The common lilac is one of the most widely observed phenological indicators in the United States because it is planted in gardens and parks across the country. It has a distinct and easily observed blooming event, and it has been recorded by amateur and professional observers for over a century. Long-term lilac phenology records in the northern United States show that the date of first bloom has advanced, become earlier, by approximately 4 to 7 days per decade in the northern Great Plains and upper Midwest since 1956. The lilacs in Minneapolis are blooming about 2 weeks earlier now than they did 60 years ago. The honeybee emergence tells a related story. Honeybee colonies begin foraging for pollen in early spring, triggered by increasing day length and warming temperatures. As spring arrives earlier, the bees are emerging earlier, but the flowers they depend on for early season pollen are also shifting their timing. The question is whether the bees and the flowers are shifting at the same rate. And the answer in many regions is no. Some spring wildflowers respond primarily to temperature and are therefore advancing their bloom dates substantially. Others respond more to day length than temperature and are therefore advancing their bloom dates little or not at all. The result is that early season foragers, bees, certain butterflies, certain flies, may emerge into a world where their usual early food sources are not yet available, or alternatively, may miss the peak of their food sources because those sources have already bloomed and passed by the time the pollinators emerge. This kind of timing mismatch, biologists call it phenological mismatch or trophic mismatch, is one of the most extensively documented ecological consequences of climate change in temperate regions. The classic study is the Great Tit in the Netherlands, where researchers discovered in the 1990s that the birds were no longer synchronized with the peak of their primary food source, caterpillars of the winter moth, because the caterpillars were advancing their emergence faster than the birds were advancing their hatching date. The birds hatch later than they used to. The caterpillars are peaking earlier than they used to. And the overlap between peak food availability and maximum chick demand is shrinking. In years of severe mismatch, chick survival falls dramatically. Similar mismatches are occurring across the United States. Migratory birds that time their arrival on the breeding grounds to coincide with the spring flush of insects. The peak of insect abundance that typically coincides with leaf out and flower blooming, are finding that the timing of that peak has shifted. Some species can adjust their migration schedule in response to changing conditions along the route. Others are locked into migration timing by physiological triggers, day length primarily, that do not change with the climate. Species with inflexible migration schedules are experiencing growing mismatches with the ecological conditions they arrive to. The monarch butterfly provides one of the most dramatic and visible examples. The monarch's annual migration cycle involves at least 4 generations. The spring generation that moves northward from Mexico, the summer generations that breed across the northern United States and southern Canada, and the fall generation that migrates back to Mexico to overwinter. The timing of the northward spring migration is keyed, in part, to the availability of milkweed, the sole plant on which monarchs can lay eggs. Milkweed availability in the spring is keyed to soil temperature and spring warmth. If spring arrives earlier, milkweed emerges earlier, but the monarchs whose spring movement northward from Mexico is triggered by a combination of temperature and day length cues in Mexico may not receive the same early signal. If they are arriving in Texas in late March to find that the milkweed has already peaked and is declining, the first breeding generation has fewer resources than it needs. This is one of several interacting factors that have contributed to the catastrophic decline of the monarch population over the past 2 decades, a decline of approximately 80 to 90% in the eastern migratory population based on overwintering colony sizes in Mexico. The phenological mismatch is not the only factor. Habitat loss, pesticide use, and climate variability on the overwintering grounds in Mexico are also implicated. But it is a real and demonstrably worsening factor. The timing shifts in phenology are not occurring at a uniform rate across all species, all regions, or all types of biological events. This is precisely what creates the mismatches. A study published in the journal Science in 2016, examining 30 years of phenological data from 500 plant and animal species across the United States, found that approximately 68% of species showed phenological shifts consistent with the direction predicted by climate warming: blooming earlier, arriving earlier, hatching earlier. But the magnitude of the shifts varied enormously across species. Some species had advanced their phenological events by 3 weeks or more. Others had barely moved. The result is that the relative timing of events that used to be synchronized, that used to happen in the same sequence, with the same spacing between them year after year, is now variable and increasingly disrupted. Chapter 4: Agriculture, when the growing season stops being predictable. American agriculture was built on seasonal predictability. The Corn Belt of Iowa, Illinois, Indiana, and Ohio, the most productive agricultural region in the world, operates on a finely tuned calendar. Plant corn too early and you risk frost damage to the seedlings. Plant too late, and the season is not long enough for the crop to reach maturity before the first fall freeze. The planting window, the period between the last spring frost and the point at which the soil is warm enough to germinate corn reliably, has historically been well defined for each location, and agricultural practices, seed varieties, and crop insurance frameworks have all been built around its historical boundaries. That window is moving, and it is not moving smoothly. The last spring freeze date in the Corn Belt has shifted approximately 1 to 2 weeks earlier over the past 5 decades, based on NOAA climate data. This seems like an unambiguous benefit: a longer frost-free growing season, more room to maneuver in the planting calendar. But the shift is accompanied by dramatic year-to-year variability that makes the earlier average date a misleading guide for planning. A region where the average last frost date has moved from May 1st to April 20th might also have seen the probability of a late season frost in the last week of April remain significant. or even increase, because the increased variability of the spring temperature pattern means that severe cold snaps can still occur after the average frost date has passed. This is the central paradox of agricultural season disruption. The average conditions are shifting in ways that seem favorable, but the variability around the average is increasing, which makes the risk of catastrophic late-season events higher, even as the average frost date moves earlier. The difference between a growing season that ends on October 1st with probability 90% and one that ends on October 15th with probability 75% and October 1st with probability 15% is not captured in the average date. It is captured in the distribution, and it is the distribution that farmers who need to make planting decisions before they know what the season will actually bring are trying to navigate. The 2012 growing season in the Midwest provided a vivid illustration of this paradox. Following an exceptionally warm winter that ended early, an unprecedented warm spell in March and early April triggered early crop planting across much of the Corn Belt. Farmers, seeing soil temperatures warm weeks earlier than usual, planted their corn and soybeans well ahead of the historical schedule. Then, in mid-April, a late cold snap struck. Not an extraordinary cold event by historical standards, but a killing frost occurring after far more crops had been planted than would normally be in the ground at that date. The losses were significant. The early season had been so warm that farmers had been effectively gambling on the frost-free period having arrived, and the late frost punished that gamble. The same dynamic has played out multiple times since. The increasingly warm and early springs lure farmers into early planting, and the occasional severe late-season cold events, which are not disappearing even as average temperatures rise, deliver disproportionate losses because more of the crop is in the ground and more vulnerable when the event occurs. The combination of earlier average conditions and maintained or increased variability is creating a more volatile risk environment for agriculture, not a simpler one. Drought has become the most consequential agricultural climate risk in the United States, and its relationship to the breakdown of seasonal patterns is direct and complex. The western United States has experienced a persistent drought that since about 2000 has been described by scientists as a megadrought, a multi-decade dry period comparable in severity to the medieval megadroughts that affected indigenous civilizations in the American Southwest before European contact. The current megadrought is driven by a combination of reduced precipitation and dramatically increased evapotranspiration, the loss of water from the landscape through evaporation from soil and surfaces, and through transpiration by plants. Evapotranspiration increases with temperature, and the consistently warmer temperatures of the past 2 decades have effectively increased the amount of moisture that the atmosphere sucks out of the western landscape during each growing season. The heat dome events that have become more frequent and more intense in the western United States. The extreme, persistent high-pressure systems that trap hot air over a region for days to weeks have catastrophic effects on agriculture. The heat dome that settled over the Pacific Northwest in late June and early July 2021 set all-time temperature records across the region. 121 degrees Fahrenheit in Lytton, British Columbia, 108 degrees in Portland, Oregon, 116 degrees in Wasco, Oregon. Washington State lost more than 80% of its Rainier cherry crop to heat damage during that event, as the fruit that was close to harvest was literally cooked on the trees. Similar events, less historically extreme, but still outside the range of what agricultural practices and infrastructure were designed to accommodate, have occurred repeatedly across the western agricultural regions. Pollination is acutely sensitive to temperature extremes. Many of the trees and shrubs that produce fruit crops, apples, pears, peaches, cherries, almonds, require a chilling requirement to produce fruit, a specific number of hours during winter when temperatures are cold enough, typically below 45 degrees Fahrenheit, to break the dormancy of the flower buds. If the winter does not provide enough chilling hours, which is increasingly common in California and the Southeast, as winters warm, the trees fail to break dormancy properly, and fruit production suffers. At the same time, a late frost after the trees have bloomed, which is more likely because warming springs are advancing bloom dates into periods when freezing temperatures can still occur, destroys the flowers, and with them the entire fruit crop for that year. California's almond industry, a $5 billion annual crop that provides about 80% of the world's almond supply, is facing both of these pressures simultaneously. The state's almond trees are blooming earlier due to warming winter temperatures, which exposes them to greater risk of spring frost damage. And in some growing regions, insufficient winter chilling is beginning to affect bloom synchrony. The trees within a single orchard are no longer breaking dormancy and blooming in a tight, synchronized window, which reduces the efficiency of pollination. The United States agricultural sector loses approximately $5 billion annually to weather and climate extremes, a figure that has been increasing over time as both the frequency and intensity of extreme events increases. The losses are not distributed randomly. They fall disproportionately on smaller operations and on production of specialty crops, fruits, vegetables, nuts, that are less amenable to geographic diversification and less protected by the crop insurance framework that covers the major commodity crops. The farmers most affected by the breakdown of seasonal predictability are often the ones with the fewest financial resources to absorb the losses. Chapter 5: Ecosystems. The clock is broken and things are dying. The phenological mismatches discussed in Chapter 3 are not just inconveniences for naturalists and bird watchers. They represent a fundamental disruption to the ecological processes that maintain the functioning of American ecosystems. The processes that purify water, regulate floods, cycle nutrients, prevent soil erosion, support food webs, and maintain the biodiversity that is the foundation of ecosystem resilience. The relationship between trees and the insects that depend on them is one of the most consequential seasonal timing relationships in temperate forest ecosystems. Many forest insects, including the bark beetles that have devastated western forests and the gypsy moth, now renamed spongy moth, that has caused widespread defoliation in eastern forests, are regulated in part by the synchronization of their life cycles with the conditions of their host trees. When that synchronization breaks down, the consequences can be catastrophic. The mountain pine beetle is native to the western United States and Canada. It has always been present in western pine forests, and its populations have always been subject to periodic outbreaks that kill patches of forest before being controlled by cold winters that kill overwintering beetle larvae in the bark of trees. The cold winters are the key. Temperatures below approximately -40 degrees Fahrenheit for sustained periods kill a significant fraction of the overwintering larvae and prevent the beetle populations from building to outbreak levels. Since the late 1990s, the cold winters that historically regulated mountain pine beetle populations have been failing to occur with sufficient frequency and intensity in much of the beetle's range. The result has been the largest forest insect outbreak in recorded North American history. An infestation that, at its peak in the late 2000s, had killed pine trees across approximately 70,000 square miles of British Columbia alone, with substantial additional mortality across the U.S. Rockies, from Colorado to Montana to Idaho. The dead trees, standing gray snags that remained for years before falling, represented an enormous accumulation of dry fuel that dramatically increased wildfire risk across the affected regions. Several of the largest and most destructive wildfires of the 2000s and 2010s burned through areas that had been killed by beetle infestation. The mountain pine beetle story illustrates a general principle that is playing out across multiple insect-tree interactions in American forests. Insects that were controlled by winter cold are expanding their ranges, surviving in higher elevations and higher latitudes, and attacking trees that were not co-evolved with them and that have no resistance to their attacks. The hemlock woolly adelgid, an invasive insect originally from Japan, kills hemlock trees by sucking sap from the base of the needles. It was introduced to the eastern United States in the 1950s and has spread northward through the Appalachians, killing hemlocks across a widening range. The northward spread has historically been limited by the cold winters of New England, which kill overwintering adelgids at temperatures below about 0 to -4 degrees Fahrenheit. As winter temperatures in New England have risen, those lethal temperature thresholds are being crossed with declining frequency, and the hemlock woolly adelgid is pushing farther north and into higher elevations, where hemlocks, which are a keystone species in their ecosystems, providing dense shade that keeps streams cold, providing habitat for a specific set of birds and other animals, cycling nutrients in specific ways, are not accustomed to this pest and have no resistance. The loss of eastern hemlock to woolly adelgid is one of the most acute ecological crises in the eastern United States, and it is a crisis that is directly accelerated by the breakdown of winter cold. The trees are large and long-lived. Hemlock forests in the southern Appalachians can be 400 to 500 years old, and once an old-growth hemlock stand is killed, the ecosystem does not simply recover. It is transformed into a fundamentally different type of forest, with different stream temperatures, different light conditions, different wildlife communities. The hemlock's role in maintaining cold, shaded streams makes it critical for the brook trout and other cold water fish species that depend on those streams. Rivers and streams throughout the United States are being affected by the changing seasonal patterns in ways that are both direct. Warmer water temperatures from warmer air temperatures and reduced shading by dying forests, and indirect changes in the timing and magnitude of streamflow as snowpack patterns change. Many western rivers are fed primarily by snowmelt, and the shift toward earlier snowmelt is changing the timing of peak flow from spring to late winter or early spring, compressing the pulse of high flow into a shorter and earlier period. This changes the availability of the cold, oxygenated water that fish and other aquatic organisms need. It changes flood timing in ways that affect riparian vegetation and the animals that depend on it. And it reduces late summer and autumn river flows, which are already the most stressful period for aquatic life in many western rivers, making that stress more severe. The Pacific salmon are among the most vulnerable species to this combination of changes. Salmon require cold water. Most salmon species are stressed at temperatures above about 65 degrees Fahrenheit, and temperatures above 72 degrees are typically lethal. Salmon also require specific flow conditions for their spawning migrations. Enough water to navigate upstream, but not so much that the fast current prevents them from reaching their spawning areas. The timing of the migration is keyed in part to the availability of cold, oxygenated water and to the flow conditions in the rivers. The combination of earlier snowmelt, which reduces late season flows, warmer summer air temperatures, which heat the rivers directly, and reduced summer precipitation, which further lowers flows in many western rivers, is creating conditions that are increasingly inhospitable for salmon during their summer and autumn migration period. The 2015 sockeye salmon disaster on the Columbia River system, in which approximately 97% of the year's returning sockeye salmon died before reaching their spawning grounds due to record-high water temperatures in the river, was a preview of conditions that are projected to become increasingly common. Wildfire is perhaps the most visible and catastrophic way in which the breakdown of seasonal patterns is transforming American ecosystems. The fire season in the western United States has lengthened by approximately 105 days since the early 1970s, based on Forest Service analysis. It used to begin in earnest in July or August and end in September or October. It now effectively runs from May or June through November or December in much of the Intermountain West, and in some Southern California locations, there is no longer a meaningful end to fire season. Large fires are occurring in January and February, months when fire activity was historically minimal. The longer fire season is driven by a combination of factors that all trace back to the seasonal disruption. Earlier snowmelt means that vegetation begins drying out weeks earlier in spring. Higher temperatures during the fire season increase the rate at which fuels dry and the severity of fire behavior. More frequent heat dome events create extended periods of extreme fire-conducive conditions. And the increasing area of dead forest, from bark beetle kill, from drought-induced mortality, from previous fire, adds to the fuel loads available for burning. The record-breaking fire seasons of 2017, 2018, 2020, and 2021, each exceeding the previous records for area burned, for structures destroyed, for deaths, and for smoke production, were not anomalies caused by careless land management or random bad luck. They were the result of a systematic shift in the conditions that drive fire behavior, a shift that is directly traceable to the changing climate and the breakdown of the seasonal temperature and moisture patterns that previously regulated fire risk. Chapter 6: Infrastructure. Built for seasons that no longer exist. American infrastructure. The roads, bridges, buildings, pipelines, power grids, stormwater systems, and water supply systems that constitute the built environment was designed and built for a specific climate. The specifications and standards that engineers use to design infrastructure are based on historical climate data. The 100-year flood level that flood infrastructure must withstand. The temperature extremes that pipes and cables must be able to handle. The precipitation intensity that drainage systems must be able to manage. The snow loads that roofs must be engineered to bear. Those historical climate data are no longer an accurate guide to future conditions. Infrastructure built to the historical standards of the 20th century is being asked to perform in a climate that increasingly falls outside those standards. Water infrastructure is among the most vulnerable. Municipal water systems in the western United States were designed around historical patterns of snowpack accumulation and snowmelt timing. A typical western city's water supply consists of a reservoir that fills primarily from snowmelt in spring, storing water to supply the dry summer and autumn. The capacity of the reservoir, the timing of release operations, and the management rules that govern the system were all optimized for a historical regime in which the snowmelt peak occurred in May or June, and summer drought was severe but predictable. As the snowmelt peak shifts earlier into March or April in many basins, the reservoirs are filling earlier in the year, which means they are reaching capacity and must begin releasing water earlier, before the peak of summer demand. In some cases, this means releasing water in late winter that could have been stored for summer use, effectively reducing the effective storage capacity of the system. In other cases, the earlier melt means more water arrives in the system during the wet season, increasing flood risk, while summer flows are lower and more prolonged drought conditions are more frequent. The city of Los Angeles gets approximately 1/3 of its water from the eastern Sierra Nevada snowpack through the Los Angeles Aqueduct system, built in 1913. That system was designed for a snowpack that is now reliably less than it used to be, and that comes off the mountains faster and earlier. Los Angeles has invested heavily in water recycling and groundwater banking to compensate. But the fundamental mismatch between the infrastructure designed for one climate and the climate it is now operating in is not fully bridgeable by operational adjustments. Power grid infrastructure is vulnerable to the changing seasonal patterns in multiple ways. Electricity demand for air conditioning is increasing as summer heat intensifies, and as heat events extend earlier and later in the season. Air conditioning load that used to begin in earnest in June now begins in some regions in April or May. At the same time, the natural gas pipelines and power-generating equipment that supply electricity during peak demand events are vulnerable to extreme heat. High temperatures reduce the efficiency of gas turbines, reduce the capacity of transmission lines, which heat up and sag under high electrical load in hot weather, and can cause grid failures at exactly the moment when demand is highest. The February 2021 winter storm that affected Texas, what became known as Winter Storm Uri, is one of the most dramatic illustrations of infrastructure built for climate conditions that are no longer reliable. Texas's power grid was built for the climate of the 20th century, in which extreme cold events in the state were rare and brief. The natural gas infrastructure, wellheads, processing facilities, pipelines, was not winterized for extended extreme cold because such events were rare enough that the cost of winterization was not considered justified by the expected frequency of use. When Winter Storm Uri brought extended, sub-freezing temperatures across Texas for multiple days, the natural gas system froze. Natural gas supply to power plants failed, and the power grid collapsed. Approximately 4.5 million households lost power. Between 250 and 700 people died from cold exposure and related causes, depending on the accounting method. The irony of Winter Storm Uri is that it was driven in part by the same atmospheric dynamics that are disrupting seasons across the country. The polar vortex, the circulation of cold air around the Arctic that normally keeps the coldest temperatures confined to the high latitudes, has become less stable as the Arctic has warmed. A warming Arctic reduces the temperature contrast between the Arctic and the mid-latitudes, which weakens the jet stream and the polar vortex. A weaker polar vortex is more prone to disruption, and when it is disrupted, it can spill cold Arctic air much farther south than normal. The severe Texas cold snap was counterintuitively connected to the warming of the Arctic, an example of how the disruption of seasonal patterns can produce effects that seem to contradict the direction of change. Stormwater infrastructure is increasingly overwhelmed by precipitation events that exceed the design capacity of the systems. Urban drainage systems, the sewers, culverts, and detention basins that manage rainwater runoff, are typically designed for the 100-year storm as it was defined by 20th century rainfall frequency statistics. But as the intensity of extreme precipitation events increases, a well-documented consequence of a warmer atmosphere holding more water vapor, events that would historically have been the 100-year storm are occurring more frequently. What was the 100-year storm in 1970 is now occurring roughly every 30 to 40 years in many regions of the eastern United States, based on updated analysis of the precipitation record. Roads, bridges, and other transportation infrastructure are affected by the changing freeze-thaw cycle. Road damage from repeated freezing and thawing, the expansion of water that seeps into pavement cracks as it freezes, is one of the primary causes of road deterioration in northern climates. As winter temperatures rise and the number of freeze-thaw cycles per winter increases, because the temperature is spending more time oscillating around the freezing point rather than staying consistently below it. Road damage is actually increasing in some northern regions despite the overall warming trend. This is another counterintuitive effect: warming that is occurring unevenly, increasing variability and the frequency of cycling through critical thresholds, rather than simply raising all temperatures uniformly. Chapter 7: The Human Experience. What people are noticing and what it costs them. The scientific record of seasonal disruption is unambiguous, but the scientific record describes averages, trends, and probabilities. What it does not fully capture is the accumulated weight of daily lived experience, the way that the breakdown of seasonal predictability presses on individual lives, livelihoods, and well-being across the country. Farmers are perhaps the group most acutely affected and most eloquently articulate about the changes they are experiencing. In interviews, surveys, and oral histories collected by agricultural extension services and research institutions, farmers across every region of the country describe a common theme: the knowledge and practices that were handed down to them by parents and grandparents, the rules of thumb for when to plant, when to harvest, when to expect rain, when to expect frost, are no longer reliable. The collective agricultural wisdom encoded in generations of farming families is becoming obsolete faster than it can be replaced with new knowledge. A corn farmer in central Iowa, whose family has farmed the same land for 4 generations, described it this way: "My grandfather could tell you the date he expected the last frost within a week, and he was right almost every year. My father was right maybe 8 years out of 10. Now I'm right to maybe 6 years out of 10, and the years I'm wrong by more." This is the statistical signature of increased variability. The average is still reasonable, but the variance around it has grown, and the tail events, the late frosts, the early droughts, the midsummer heat events, are more frequent and more severe. Ski resorts in the Northeast and the Pacific Northwest are facing an existential challenge from the shrinking ski season. The number of skiable days per year, days on which natural snow conditions or reliable snowmaking conditions exist, has decreased substantially in many mountain regions. In New England, the ski industry has invested heavily in snowmaking infrastructure to compensate for reduced natural snow. But snowmaking requires temperatures below freezing, something that is occurring less reliably in the shoulder seasons that were historically the most productive for snowmaking. The operational window for snowmaking has compressed, the cost has increased, and the probability of a genuinely poor ski season due to insufficient cold in the critical December-January period has increased. Beekeepers across the country are struggling with what they call spring confusion, the phenomenon in which warming winter temperatures trigger honeybee colonies to begin increasing their brood rearing earlier than historically, which increases the colony's need for food, which can lead to starvation if the early spring foraging is disrupted by a late, cold snap, or if the spring nectar flow does not materialize at the expected time. The interaction between colony biology, which responds to temperature, and plant phenology, which responds to a combination of temperature and day length, creates windows of vulnerability that are more frequent and more severe as the seasonal temperature pattern becomes less predictable. Wildfire smoke has become a new season in the western United States. What was once a phenomenon confined to occasional days in August and September has become a presence that stretches from May to November, with smoke from fires burning hundreds of miles away, or from fires burning simultaneously across multiple states, blanketing cities, closing schools, canceling outdoor events, and contributing to respiratory health problems across a wide population. The health costs of smoke exposure are substantial. Wildfire smoke is more chemically complex and more toxic than other forms of air pollution, containing fine particulate matter and hundreds of toxic compounds from burning vegetation, soil, and structures. The economic costs of the seasonal disruption are distributed widely but unevenly. The National Oceanic and Atmospheric Administration estimates that weather and climate disasters cost the United States approximately $150 billion per year over the past 5 years, roughly triple the rate of the 1980s and 1990s. But these headline figures capture only the direct costs. The value of destroyed property, crops, and infrastructure. They do not capture the indirect costs, the increased insurance premiums that reflect rising risk, the higher food prices that result from crop failures, the healthcare costs from heat-related illness, respiratory disease from wildfire smoke, and mental health consequences of repeated extreme events, the cost of rebuilding after floods and fires that are occurring with increasing frequency in the same locations. The mental health consequences of repeated climate disruption are increasingly recognized by researchers. A study published in the Proceedings of the National Academy of Sciences in 2018 found that warmer monthly average temperatures in the United States were associated with increased rates of mental health issues, including depression and anxiety. Wildfire survivors show high rates of post-traumatic stress disorder. Farmers experiencing repeated crop failures report elevated rates of anxiety, depression, and financial stress. The psychological costs of living in an environment that is increasingly unpredictable and increasingly threatening are real and are adding to the total burden that the breakdown of seasonal patterns is imposing on American communities. Chapter 8: The Science of Why. What is driving the breakdown? The disruption of seasonal patterns across the United States is not random, and it is not mysterious. It has specific, well-understood physical causes that operate through specific mechanisms, producing the specific patterns that the data shows. Understanding those causes is not just academically important. It is the only way to understand how the disruption will continue to evolve, which determines what kinds of adaptation are possible and what kinds are futile. The foundational cause is the increase in atmospheric greenhouse gas concentrations, primarily carbon dioxide and methane, driven by the burning of fossil fuels and land use change. The basic physics of this effect has been understood since the 1850s, when the physicist Eunice Newton Foote conducted experiments demonstrating that carbon dioxide absorbs heat radiation, and since the 1860s, when John Tyndall quantified the greenhouse effect of various atmospheric gases. The physics has been confirmed and refined by more than 170 years of subsequent research, and it is not in dispute in the scientific literature. Increasing atmospheric CO2 concentrations cause the atmosphere to retain more heat, warming the surface. The current atmospheric CO2 concentration is approximately 420 parts per million, a level not seen in the Earth's atmosphere in at least 3 million years, based on ice core and sediment records. The rate at which it is increasing, approximately 2.5 parts per million per year, is faster than any natural rate of CO2. Increase in the geological record, including the large-scale volcanic eruptions that have driven mass extinction events. The physical consequence is a warming atmosphere, and the ecological consequence is the seasonal disruption described throughout this video. But why does increased CO2 cause the specific pattern of seasonal disruption described here? Faster warming in winter than in summer, faster warming in the Arctic, the breakdown of seasonal predictability. The answer lies in the specific physics of how the additional heat trapped by greenhouse gases interacts with the different physical systems of the Earth's climate. The Arctic amplification effect explains why the northern latitudes have warmed faster than the tropics, and why winter has warmed faster than summer. The Arctic Ocean, which for most of the recent geological history of the Earth has been covered by sea ice year-round, has been losing that sea ice cover over the past several decades. Sea ice is highly reflective. It reflects approximately 80 to 90% of incoming solar radiation back to space. Open ocean water is much less reflective. It absorbs approximately 90% of incoming solar radiation. As sea ice is lost, the Arctic absorbs more solar energy, which causes further warming, which causes further ice loss in a self-reinforcing feedback loop. This Arctic amplification means that the Arctic has warmed approximately 3 to 4 times faster than the global average over the past 50 years. The warming of the Arctic has a direct effect on the atmospheric circulation patterns that determine weather at mid-latitudes, including across the continental United States. The jet stream, the high-altitude current of fast-moving air that circles the northern hemisphere at mid-latitudes, roughly separating cold, Arctic air from warmer subtropical air, is driven by the temperature contrast between the Arctic and the tropics. As the Arctic warms faster than the tropics, this temperature contrast decreases and the jet stream slows down and becomes more prone to large amplitude meanders, the kind of looping north-south excursions that pull cold Arctic air deep into mid-latitudes and push warm subtropical air far north. These amplified jet stream meanders are directly responsible for several of the most alarming patterns of seasonal disruption. When the jet stream loops far to the south, it can pull Arctic air into Texas in February, producing the kind of event that caused the 2021 power crisis. When it loops far to the north, it can pull subtropical air deep into the continent, producing the kind of February heat waves that have increasingly confounded the upper Midwest and Northeast. The larger the amplitude of the jet stream meanders, the greater the variability of mid-latitude weather, and the greater the disruption of seasonal predictability. The science of jet stream behavior and its relationship to Arctic warming is an active and sometimes contested area of research. Some scientists argue that the connection between Arctic warming and increased jet stream waviness is clear and well established. Others argue that the signal is weaker than claimed, and that natural variability in the jet stream is the primary driver of the observed patterns. The debate is real, and the scientific literature reflects genuine uncertainty. What is not in dispute is that the observed changes in mid-latitude weather variability are real, that Arctic warming is real, and that the physical mechanisms by which Arctic warming affects the jet stream are theoretically well-grounded. The question is about the magnitude of the effect relative to natural variability, not about whether the effect exists. Atmospheric moisture content is another critical driver of the specific patterns of seasonal disruption. A warmer atmosphere holds more water vapor. The Clausius-Clapeyron equation, a fundamental relationship in atmospheric thermodynamics, tells us that for every degree Celsius of warming, the atmosphere can hold approximately 7% more water vapor. This means that when precipitation occurs in a warmer world, there is more moisture available in the atmosphere, and the precipitation events are more intense. It also means that the atmosphere is more effective at pulling moisture out of the land surface during dry periods, increasing evapotranspiration and making droughts more severe even when precipitation amounts do not change. The specific regional patterns of drought and flooding that are emerging across the United States reflect this dynamic. The western United States is experiencing drought that is driven not primarily by reduced precipitation, but by dramatically increased evaporative demand. The atmosphere is hungrier for moisture, and it is pulling it out of soils, vegetation, and snowpack at a faster rate. The eastern United States is experiencing more intense flooding events, not necessarily more frequent precipitation, but more intense precipitation when it does occur, producing runoff events that exceed the capacity of natural and engineered drainage systems. The increased atmospheric moisture content is not just a statistical property of the changed climate. It manifests in specific, observable ways in extreme weather events. Atmospheric rivers, the long, narrow corridors of concentrated moisture that flow from the tropics to mid-latitudes and are responsible for a large fraction of the precipitation in California and the Pacific Northwest, are becoming more intense as the warmer atmosphere holds and transports more water vapor. The atmospheric rivers that struck California in the winter of 2022 to 2023, a series of bomb cyclone systems that delivered record precipitation after multiple years of extreme drought, illustrated the weather whiplash pattern that climate scientists have long projected. In a matter of weeks, the state went from drought conditions so severe that Governor Newsom had declared an emergency to flooding conditions that killed 20 people, caused billions of dollars in infrastructure damage, and overwhelmed water management systems designed for a climate where such extremes did not arrive so quickly or so intensely. The heat dome events that have become more frequent and more intense in the western United States are also explicable through the changed atmospheric dynamics. A heat dome forms when a high-pressure system parks over a region and traps heat near the surface. The intensification of heat domes in recent years is linked both to the warmer baseline temperatures, there's more heat to trap, and to the changed jet stream behavior associated with Arctic warming. The jet stream meanders that allow these high-pressure systems to remain stationary over a region for extended periods rather than being swept along by the normal westerly flow. The combination of a warmer baseline, more atmospheric moisture, changed jet stream dynamics, and the loss of reflective snow and ice cover creates the conditions for weather events that fall outside the historical range, not occasionally, but increasingly as a regular feature of the seasonal pattern. El Niño and La Niña, the periodic warming and cooling of the tropical Pacific Ocean that drive year-to-year variations in weather patterns across North America, continue to operate against the background of long-term climate change and contribute to the interannual variability that makes seasonal patterns difficult to predict from year to year. The interaction between El Niño/La Niña variability and the long-term warming trend means that the worst drought years in the West and the most extreme precipitation years in the East are becoming more extreme than they would be under either influence alone. The background state is changing while the natural oscillations continue, and the combination produces a range of outcomes that increasingly falls outside the historical experience. Chapter 9: Regional Deep Dives. What each part of the country is experiencing. The national average obscures the profound regional diversity of seasonal disruption across the United States. Different regions are experiencing the breakdown of seasonal patterns in different ways, through different mechanisms, with different consequences for the people and ecosystems that depend on them. The Northeast, New England, and the Mid-Atlantic is experiencing some of the most dramatic changes to winter character of any region in the country. The number of days per year with snow on the ground in the Northeast has decreased by approximately 20% since 1970. The ski industry in New England is facing a fundamental challenge to its viability in a warmer world. The resort towns of Vermont, New Hampshire, and Maine have built their economies around winter tourism, and winter is becoming shorter, less reliable, and more expensive to artificially maintain. Ice fishing, maple syrup production, the cycle of ice in and ice out on lakes that has structured the rhythms of northern New England communities for generations, all are shifting. The maple syrup industry is a particularly sensitive indicator of seasonal change in the Northeast. Maple syrup production depends on a specific weather pattern: cold nights below freezing, followed by warm days above freezing, typically in February and March. This freeze-thaw cycle drives the sap flow in sugar maple trees that producers tap for syrup. As winter's warm and spring arrives earlier, the maple sap season is shifting earlier and becoming shorter. Climate models project that by 2100, if greenhouse gas emissions continue at current rates, the core maple syrup production area will have shifted northward by several hundred miles, leaving much of Vermont and New Hampshire outside the viable production zone. Spring in the Northeast now regularly delivers dramatic oscillations, periods of midwinter warmth that trigger premature plant growth, followed by sharp cold snaps that destroy what has emerged. The lilac hedgerows that used to bloom reliably in early May in southern New England are now blooming in mid-April, exposed to the heightened risk of April frost events. The forsythia that used to signal the reliable onset of spring now blooms in late February or March and has sometimes been struck by late-season snowstorms. The Southeast is experiencing seasonal disruption that is less visible in terms of snow and ice, but equally consequential in its ecological and agricultural effects. The subtropical humidity that has historically defined the South's climate is intensifying, with more extreme summer heat-humidity combinations that push the feels-like temperature to dangerous levels for outdoor workers. The growing season in the Deep South is now year-round in many locations. Not necessarily a benefit, since it also means year-round pest pressure and year-round need for irrigation without the winter-killing frost that has historically controlled many agricultural pests and diseases. The peach industry in Georgia and the Carolinas, one of the defining agricultural traditions of the Southeast, is under severe stress from insufficient winter chilling. Georgia peaches require approximately 750 to 800 hours of temperatures below 45 degrees Fahrenheit to break dormancy and produce fruit normally. As winters warm, the chilling requirements are increasingly not being met, and the trees are producing reduced crops or failing to bloom normally. the area of viable peach production in Georgia has contracted significantly, and some growers have begun transitioning to low-chill varieties or abandoning peach production entirely. The Southeast is also on the front line of increasing hurricane activity that is being supercharged by warmer ocean temperatures. Hurricanes draw their energy from warm ocean surface water, and as the Gulf of Mexico and the western Atlantic warm, the storms that form over them are more likely to undergo rapid intensification. The sudden strengthening of a hurricane from manageable to catastrophic within a period of 24 to 48 hours that repeatedly catches coastal communities off guard. The relationship between hurricane season and the broader seasonal calendar is also shifting. The hurricane season has effectively lengthened at both ends, with storms forming earlier and persisting later into autumn than historical patterns. The Midwest is experiencing the paradox of agricultural disruption most acutely. The Corn Belt states, Iowa, Illinois, Indiana, Ohio, and Minnesota, are seeing the planting calendar shift earlier, the growing season lengthen, and the average conditions become more favorable for crop growth by some metrics, while simultaneously becoming more volatile and unpredictable. The frequency of late spring and early summer droughts is increasing, and when they occur during the critical pollination period for corn, typically the third week of July in the core Corn Belt, the yield losses can be catastrophic. The 2012 drought reduced U.S. corn yields by approximately 13% from the previous year, contributing to a global commodity price spike that affected food security in developing countries. The summer heat in the Midwest is intensifying, with humid heat events that are particularly dangerous for human health because high humidity prevents the evaporative cooling that allows the human body to tolerate high temperatures. The number of days per summer when the heat index, the apparent temperature accounting for humidity, exceeds 100 degrees Fahrenheit is increasing across much of the Midwest. For outdoor workers, agricultural workers, construction workers, utility workers, these conditions represent a genuine occupational health hazard. Heat-related illness and death among outdoor workers is increasing, and the peak of heat stress is shifting earlier in the summer season. The Great Plains are experiencing a transition that may be one of the most consequential long-term shifts in American agricultural geography. The Southern Plains, Texas, Oklahoma, and Kansas are becoming hotter and drier, with the warming occurring faster than precipitation is declining, but the combined effect of both trends dramatically increasing drought stress. The Northern Plains, the Dakotas, Montana, and Nebraska are also warming rapidly, though with somewhat more complex precipitation trends. The entire region is seeing increased wildfire risk as vegetation dries and fire seasons lengthen. The Ogallala Aquifer, the massive underground water reserve that underlies much of the Great Plains and supplies irrigation for approximately 30% of the nation's groundwater irrigated agricultural land, is being depleted at rates that far exceed its natural recharge. The aquifer's depletion is being accelerated by the increasing drought stress that is driving more intensive irrigation, and the regions where the aquifer is shallowest, the southern high plains of Texas and Kansas, are seeing well failures at an accelerating rate. The loss of the Ogallala would fundamentally transform the agricultural landscape of the Great Plains, but the transition is being driven in part by the changed seasonal conditions that are making dry land farming less viable in the region. The Mountain West, Colorado, Utah, Wyoming, and Montana is experiencing the most dramatic changes to the fundamental water cycle of any region in the country. The Rocky Mountain snowpack, which is the primary water storage system for much of the western United States, has declined by 15 to 30% since the mid-20th century in most basins. The snowmelt peak is occurring 2 to 4 weeks earlier than historical averages in most western river systems. The Colorado River, which supplies water to approximately 40 million people in 7 U.S. states and Mexico, has been in deficit, being used faster than it is being replenished for most of the past 2 decades, resulting in the dramatic decline of Lake Mead and Lake Powell, the 2 largest reservoirs in the United States, to levels not seen since they were first filled. Before reaching the Pacific coast, the Pacific Northwest deserves specific attention because it represents the most dramatic single demonstration of seasonal disruption in American history. The June-July 2021 heat dome event, the same event that produced 121 degrees Fahrenheit in Lytton, British Columbia, was not simply an extreme weather event. It was a qualitative departure from the historical range of conditions that the Pacific Northwest had ever experienced. The Pacific Northwest's entire ecological character is built around its cool, wet maritime climate. The region's temperate rainforests, the Hoh rainforest in Washington, the forests of the Oregon coast, range, depend on abundant moisture and mild temperatures. The region's agricultural identity, its wine grapes, its soft fruits, its world-famous berries, depends on long, mild growing seasons without extreme heat. The region's urban infrastructure, Seattle, Portland, was built for a climate in which temperatures above 95 degrees Fahrenheit are so rare that the dominant design philosophy assumed air conditioning was unnecessary. During the heat dome, Portland reached 116 degrees Fahrenheit on June 28, 2021. The prior all-time record for Portland was 107 degrees Fahrenheit. The new record exceeded the old one by 9 degrees. Not a marginal exceedance, but a fundamental departure. The heat killed an estimated 1 billion marine organisms in the intertidal zone along the Pacific coast. Mussels, barnacles, sea stars, sea snails literally cooked in their shells as the rock surfaces reached temperatures exceeding 130 degrees Fahrenheit. These organisms are not replaced. Quickly, the intertidal zone communities that were established over decades were destroyed in 72 hours. Subsequent surveys found that the affected intertidal areas showed dramatically reduced organism density and species diversity for years afterward. The Pacific coast is experiencing a seasonal transition that is particularly visible because of the contrast between its wet and dry seasons. California, which has an essentially Mediterranean climate with a wet winter and a bone-dry summer, is experiencing intensification of both the wet season and the dry season, a pattern that researchers have called weather whiplash or precipitation whiplash. Years of extreme drought alternate with or rapidly succeed years of extreme precipitation, and the transition between drought and flood can occur within a single season. The atmospheric rivers, long, narrow bands of concentrated moisture in the atmosphere, often referred to as the rivers in the sky, that provide the bulk of California's annual precipitation are becoming more intense and more episodic, delivering more water in fewer events. The flood control infrastructure and water storage systems built for the historical precipitation distribution are poorly suited to handling the new pattern of infrequent, extreme precipitation events. Chapter 10: The Feedback Loops. Why it gets worse on its own. One of the most alarming aspects of the breakdown of seasonal patterns is that several of the consequences of that breakdown are themselves causes of further breakdown. The climate system contains feedback mechanisms, processes in which a change in one element of the system amplifies the original change, creating self-reinforcing cycles that can accelerate the disruption beyond what the initial forcing alone would produce. The albedo feedback, the loss of reflective surfaces, is the most quantitatively significant positive feedback in the current climate system. Snow and ice are highly reflective, returning most incoming solar radiation to space. As snow cover decreases and ice melts, the land and ocean surfaces they reveal are much less reflective and absorb much more solar energy. This additional energy absorption warms the surface further, causing more snow and ice loss, which causes more absorption. The Arctic sea ice loss is the most dramatic current expression of this feedback, but it operates at smaller scales wherever seasonal snow cover is declining, including across much of the northern United States. The permafrost carbon feedback is one of the most consequential and least understood feedback loops in the climate system. Permafrost, ground that remains frozen year-round, underlies approximately a quarter of the northern hemisphere's land area, including large portions of Alaska and the subpolar regions of Canada. Permafrost soils contain enormous quantities of organic carbon, plant material from past millennia that decomposed only partially before being frozen. As permafrost thaws in response to warming, this organic material is exposed to microbial decomposition, releasing carbon dioxide and methane, both greenhouse gases. The release of these gases from thawing permafrost adds to the atmospheric concentration of greenhouse gases, causing further warming, causing further permafrost thaw. The magnitude of the permafrost carbon feedback is highly uncertain, but the quantities involved are genuinely alarming. It is estimated that permafrost soils contain approximately twice as much carbon as is currently in the atmosphere. If significant fractions of this carbon are released over the coming decades and centuries, the feedback could substantially accelerate the warming beyond what is projected from human emissions alone. The Alaska permafrost, which is thawing faster than anywhere in the world, is already showing signs of this feedback. In some regions, the permafrost is releasing more carbon annually than the Alaskan. Vegetation is absorbing through photosynthesis, making the state a net carbon source. The forest mortality feedback is particularly relevant to the seasonal disruption story in the continental United States. As forests die from drought, fire, bark beetles, and other climate-driven stressors, they release the carbon they have stored over decades or centuries, both from immediate combustion during wildfire and from the slow decomposition of dead wood and soil carbon. A forest that was formerly a carbon sink, absorbing CO2 from the atmosphere through photosynthesis, becomes a carbon source when it dies. The large-scale forest mortality events occurring across the western United States, the bark beetle outbreaks, the drought-related die-offs, the megafires, are collectively converting Western forests from a net carbon sink to a net carbon source in some analyses. This creates a particularly disturbing feedback for the seasonal disruption story. The dying of Western forests as a consequence of the seasonal disruption, the extended droughts, the intensified fire seasons, the pest outbreaks enabled by warmer winters, is releasing carbon that contributes to the atmospheric CO2 increase that is driving the seasonal disruption. The forests are being killed by the disruption and then exacerbating it in their death. The water vapor feedback is the largest positive feedback in the current warming. As the atmosphere warms, it holds more water vapor, and water vapor is itself a greenhouse gas, actually a more potent greenhouse gas than CO2 by molecule. Though less important overall, because its concentration in the atmosphere is controlled by temperature rather than by human emissions. The additional water vapor trapped by initial CO2-driven warming amplifies that warming substantially, roughly doubling it compared to what CO2 alone would produce. This feedback operates relatively quickly. Water vapor equilibrates with the atmospheric temperature in a matter of days, and is well understood and quantified by climate models. The drought-fire-drought feedback is particularly relevant to the seasonal disruption story in the American West. Drought dries vegetation, making it more combustible. Fire removes vegetation, exposing the soil to direct sunlight and wind, increasing evaporation and reducing the moisture-holding capacity of the landscape. The burned, denuded landscape is more prone to subsequent drought stress, and the reduced vegetation means less transpiration, less movement of water from the soil to the atmosphere through plant processes, which can affect local precipitation patterns. The more drought-stressed and fire-prone the landscape becomes, the more likely future droughts and fires are to occur in the same locations. Each of these feedbacks operates on a different timescale. The albedo feedback from snow and ice loss is operating right now at the current level of warming and is accelerating. The warming in real time. The permafrost carbon feedback is beginning to operate at detectable levels, but will become more significant over the coming decades and centuries as permafrost thaw progresses. The forest mortality feedback is operating on the timescale of individual extreme events. Each major wildfire season or bark beetle outbreak changes the carbon accounting of the affected region immediately. The cumulative effect of these feedbacks is to make the baseline trajectory of climate change, and with it the disruption of seasonal patterns, worse than the direct effect of human emissions alone would produce. Chapter 11. What adaptation actually looks like, and its limits. The disruption of seasonal patterns across the United States is already committed to some extent. The greenhouse gases already emitted will continue warming the planet for decades, even if emissions stopped tomorrow, due to the thermal inertia of the ocean and the atmosphere. This means that adaptation, adjusting human systems, infrastructure, and practices to function in the new seasonal reality is not optional. It is happening or it is failing, and the consequences of failure are already visible. Agriculture is the sector that has invested most heavily in adaptation out of immediate economic necessity. Farmers across the country are changing the varieties they grow, the planting dates they use, the irrigation practices they employ, and in some cases, the crops they grow entirely. The Corn Belt of the Midwest is shifting northward. Minnesota and the Dakotas, which historically had growing seasons too short for corn, are now planting corn with higher frequency. Southern states that historically grew winter wheat are now growing it in a shorter, more uncertain window, and some are transitioning to spring wheat or abandoning wheat entirely in favor of crops better suited to longer, hotter summers. Seed companies have responded to the changing growing season by developing and marketing varieties adapted to longer seasons, higher temperatures, and greater drought stress. The introduction of drought-tolerant corn varieties, enabled by conventional plant breeding, and in some cases genetic modification, has provided some protection against the increasing drought risk in the Corn Belt. The development of heat-tolerant crop varieties for fruits and vegetables is a more challenging problem because many of the quality characteristics that make specific varieties valuable, the flavor, texture, and appearance that consumers expect, are affected by growing temperature in ways that are difficult to preserve while also improving heat tolerance. Water management adaptation is perhaps the most urgently needed and most technically challenging area of seasonal adaptation. The Western United States faces a fundamental mismatch between its water supply infrastructure, designed for the historical snowpack-dominated hydrology, and the precipitation-dominated, more episodic hydrology that the changing climate is producing. Adapting to this new hydrology requires a combination of infrastructure modification, increasing reservoir capacity to capture more precipitation during the wet season and store it for the dry season, improving the efficiency of conveyance and distribution systems, investing in water recycling and groundwater banking, and demand reduction, water-efficient irrigation, drought-tolerant landscaping, reduced consumptive use in industry and municipalities. California has made significant investments in all of these areas following the extreme droughts of 2012 to 2017 and 2020 to 2022. The state's water recycling capacity has expanded substantially. Groundwater banking, storing water in aquifers during wet years for withdrawal during dry years, is becoming more widely practiced. The agricultural sector has invested heavily in drip irrigation and precision irrigation technology that reduces water use per unit of crop produced. But the fundamental constraint is physical. There is only so much water available, and the demand for it exceeds the sustainable supply across most of California, regardless of how efficiently it is used. Forest management adaptation to the new fire reality is one of the most contentious and consequential challenges facing American environmental management. The accumulation of dense vegetation in western forests, partly a result of a century of aggressive fire suppression, which prevented the low-intensity fires that historically maintained open forest conditions, has created fuel loads that drive the catastrophic, uncontrollable megafires that have become the defining environmental crisis of the American West. The ecological restoration of fire-adapted forest conditions through prescribed burning, mechanical thinning, and the management of lightning-caused fires under conditions when they can be controlled and widely recognized as necessary, but it is politically, logistically, and resource limited. The scale of the challenge is stark. The U.S. Forest Service estimates that approximately 80 to 100 million acres of national forests need fuel treatment, prescribed burning and mechanical thinning to reduce catastrophic fire risk. At the current rate of treatment, it would take decades to address the backlog. The resources required to dramatically accelerate the treatment program are not currently available, and the window for conducting prescribed burns safely is shrinking as the fire season lengthens and the weather conditions that allow controlled burning become less frequent. Infrastructure adaptation faces the fundamental challenge that most infrastructure is designed for a 50 to 100-year service life, and the design specifications are based on historical climate data. Adapting existing infrastructure to a changing climate is far more expensive and disruptive than incorporating climate projections into the design of new infrastructure. The economic case for adaptation, the cost of building to higher standards, now versus the cost of damage and replacement under the conditions that will actually prevail, is increasingly compelling. But translating that economic case into actual changes in design standards, building codes, and investment priorities is a slow political and regulatory process. Indigenous communities across the United States are experiencing the breakdown of seasonal patterns in ways that are particularly acute, because they often maintain deep and systematic knowledge of regional ecosystems that allows them to detect subtle changes that would not be visible in conventional monitoring. Tribal nations across the Pacific Northwest have been documenting changes to the salmon runs, the backbone of their cultural and economic life, for decades, tracking not just the numbers, but the timing, the size, the condition, and the species composition of the runs with a precision that rivals scientific monitoring. What they are documenting is a systematic shift in the run timing, the increasing die-offs from heat stress, and the transformation of rivers that have sustained their communities for millennia. The Lummi Nation in Washington state has been involved in a decades-long effort to restore salmon runs to the Nooksack River system, investing in habitat restoration, water temperature management, and salmon release programs. But the fundamental conditions, warmer water temperatures, reduced summer flows, degraded water quality, are moving faster than restoration can compensate. The tribe's relationship to the salmon, which is not merely economic but spiritual and cultural in ways that are difficult to translate into the language of environmental impact assessment, is being severed not by any single catastrophic event, but by the slow grinding transformation of the seasonal conditions that make the salmon runs possible. Similar patterns are documented among tribal nations in the Great Plains, where the traditional knowledge encoded in the timing of seasonal ceremonies keyed to the flowering of specific plants, the arrival of specific bird species, the movement of specific animal populations, is no longer synchronized with the ecological events that were supposed to trigger them. The phenological shifts that scientists measure in their databases are, for indigenous communities, disruptions to ceremonies, disruptions to traditional foods, and disruptions to the ecological knowledge systems that have sustained their cultures for thousands of years. The most honest assessment of adaptation is that it can reduce the costs of seasonal disruption substantially, but cannot eliminate them. There are physical limits to how much any human system can adjust to conditions that are moving outside the range for which it was designed. A farmer can shift planting dates, switch crop varieties, and invest in irrigation. But if summer temperatures regularly reach levels that prevent corn from producing viable pollen, the adaptation options for corn production in that region are exhausted. A water manager can optimize operations, invest in storage, and reduce demand. But if the total water available in the system falls below the minimum required to sustain the population it serves, the adaptation options are exhausted. A wildfire manager can treat fuels, coordinate evacuation plans, and deploy firefighting resources. But if the fire weather conditions are such that any ignition produces uncontrollable fire behavior, the adaptation options are exhausted. The limits of adaptation are not fixed. They depend on how much the climate changes. Modest changes can be adapted to. Severe changes produce conditions that are beyond human systems' ability to adjust to, and the populations and ecosystems that depended on those systems face displacement, collapse, or transformation on a scale that constitutes genuine human suffering and ecological loss. Chapter 12. The Timeline. How quickly is this accelerating? The disruption of seasonal patterns described throughout this video is not a future problem. It is a present problem, but it is also not a static problem. The rate of change is itself changing, and the evidence of the past decade suggests that the change is accelerating faster than the previous decade's models had projected. The 2018 U.S. National Climate Assessment, the most comprehensive and authoritative assessment of climate change impacts on the United States, identified temperature trends across the country that have since been exceeded in the years following the report's publication. The frequency and intensity of heat waves in the years from 2018 to 2024 exceeded the projections made in 2018 for that same period. The wildfire seasons of 2020 and 2021 set records that the 2018 projections did not anticipate at this date. The drought that has gripped the American West has been both more severe and more sustained than the 2018 projections suggested was likely at current levels of warming. This pattern, observed reality exceeding projections, has been documented across multiple aspects of the climate system. Arctic sea ice loss is occurring faster than the models projected. Sea level rise is occurring faster than the models projected. The frequency of extreme precipitation events in the eastern United States is increasing faster than the models projected. The permafrost is thawing faster than the models projected. The pattern suggests that the climate system is responding to the forcing from greenhouse gas emissions at the high end, or sometimes beyond the high end, of the range of model projections. The implications of this pattern for the timeline of seasonal disruption are significant. If the change is occurring faster than the models projected, if the models are underestimating the rate of change, then the timeline for reaching specific thresholds of disruption is shorter than the models suggested. The 1.5 degrees Celsius warming threshold that the Paris Agreement identified as the target to avoid the most severe climate impacts was reached globally in 2024, a decade earlier than the median of model projections made in 2016. The rate of warming is accelerating, not decelerating, despite the significant investments in renewable energy and energy efficiency that have occurred over the past decade. Before addressing what these projections mean for the disruptions described in this video, it is worth being precise about where current trajectories actually sit, because this is frequently misrepresented in both directions. Both overstated by those who want to convey maximum alarm, and understated by those who want to minimize the urgency. Global greenhouse gas emissions in 2024 are higher than they were in 2015, when the Paris Agreement was signed. They are higher than they were in 2019, just before the COVID-19 pandemic temporarily reduced them. Despite the massive growth in renewable energy deployment, solar and wind power together are now adding more new electricity generation capacity globally than all fossil fuels combined. The growth in energy demand has outpaced the growth in clean energy, and fossil fuel combustion has not yet declined. The trajectory is improving, the rate of growth in emissions has slowed, and several credible analyses project that global emissions may peak sometime in the 2020s. But the current trajectory, even with the policies that are currently in place, leads to approximately 2.5 to 3 degrees Celsius of warming by the end of the century. Not 1.5, not 2, but 2.5 to 3. The policies needed to reach the 1.5 degree target are not currently in place in any major emitting country. The 2.5 to 3 degree scenario is not the apocalyptic high emission scenario, but it is not the manageable low emission scenario either. It is a middle path that implies continued accelerating seasonal disruption throughout the 21st century, with conditions by 2100 that are substantially more severe than current conditions, but not as severe as the extreme projections. Understanding where current trajectories actually lead is important context for evaluating what adaptation can realistically accomplish and what mitigation is still capable of preventing. What does this mean for the specific seasonal disruptions described in this video? It means that the changes already observed are not the end state. They are an intermediate state in a trajectory that, under current policies and emissions trajectories, will produce substantially more severe disruption over the coming decades. The frost-free growing season that has lengthened by 2 weeks over the past 40 years may lengthen by another 2 to 4 weeks in the next 20 years. The drought that is currently classified as severe across much of the West may be reclassified as moderate in 20 years when conditions are worse. The wildfire seasons that are now considered extreme by historical standards may be considered average in 20 years as the fire environment continues to shift. The specific rate at which these changes occur depends primarily on one variable: the trajectory of global greenhouse gas emissions. The relationship between emissions and warming is well established. More emissions produce more warming, and less emissions produce less warming. The scenarios used by climate scientists to project future conditions range from high emissions scenarios, in which global emissions continue to grow through the middle of the century, to low emissions scenarios, in which global emissions fall rapidly to near zero by mid-century, reflecting a rapid and comprehensive global energy transition. The projected outcomes in 2100 under these different scenarios range from approximately 1.5 to 2 degrees Celsius of additional warming beyond current levels in the lowest emissions scenario to 3 to 5 degrees Celsius in the highest emissions scenario. The difference between these outcomes, in terms of the disruption of seasonal patterns across the United States, is not a difference of degree, it is a difference in kind. The disruption already occurring at current levels of warming, the phenological mismatches, the agricultural volatility, the wildfire intensification, the infrastructure failures, is substantially less severe than what the high emissions scenario projects for the end of the century. In the high emissions scenario, climate projections suggest that the American Southwest will experience drought conditions that would be described, under current norms, as unprecedented mega droughts, that the Gulf Coast and much of the Southeast will experience heat-humidity combinations that are physiologically dangerous for extended periods during the summer, that the Corn Belt may lose its status as the world's most productive agricultural region as summer temperatures regularly exceed the thermal tolerance of corn during pollination, and that wildfire seasons in the West may be functionally permanent. In the low emissions scenario, these outcomes are substantially less severe. The disruption is real and significant. The commitments already made to the atmosphere by past emissions guarantee continued disruption even in the best-case scenario, but it is manageable through adaptation in a way that the high emissions scenario is not. This is the timeline that matters, not the timeline of what has happened, which is visible and documented. The timeline of what will happen depends on choices that are being made right now in the aggregate decisions of governments, industries, and individuals about how quickly and comprehensively to reduce greenhouse gas emissions. The disruption of the seasons is not a completed story. It is a story in progress, and the trajectory of the next chapter depends on what we do. Conclusion: the rhythm and what we lose. When it goes, the seasons are not just a meteorological phenomenon. They are the rhythm that organizes life, not just human life, but all life in temperate regions. The annual cycle of cold and warmth, wet and dry, dormancy and growth is the temporal structure within which millions of species have evolved over millions of years. The framework within which human civilizations have built agricultural systems, cultural practices, economic structures, and entire ways of understanding time and place. When that rhythm breaks down, when the seasons become less predictable, less distinct, more variable, more extreme, the loss is not just practical. It is something more fundamental. It is the loss of the temporal order that makes long-term planning possible, that allows a farmer to trust that planting now will yield a harvest later, that allows a forest to trust that the insects will emerge when the trees leaf out, that allows a species of bird to trust that if it flies north in April, it will find food when it arrives. The practical consequences documented throughout this video are real and are accelerating. The crop failures, the infrastructure breakdowns, the ecosystem collapses, the ecological mismatches that are reducing biodiversity and productivity across the country. These are not future scenarios. They are present realities, occurring in every state, affecting every sector of the economy and every aspect of the natural world. But there is also a deeper loss that is harder to quantify and more difficult to talk about in a scientific context, but that is nonetheless real. The loss of the sensory certainty that defined seasons for all of previous human history. The certainty that autumn smells a particular way, that the light in October is qualitatively different from the light in July. That the first morning, when you can see your breath, marks a specific transition in the year. These certainties are dissolving. They have not dissolved yet in most places. The seasons still exist, still arrive, still have character, but they are becoming less reliable, less sharp, less trustworthy as guides to what will come next. The awareness that the seasons are changing is spreading through the population faster than the scientific evidence itself, because people are experiencing it directly. They are noticing that the lilacs bloomed too early and got killed by a late frost. They are noticing that the October that used to be cool and crisp is now warm and prolonged. They are noticing that the snow that used to be reliable in December is now a sometime thing. They are making these observations without datasets or analysis, through the simple accumulation of experience and the comparison of that experience against memory and expectation. That noticing matters. There is a word for the distress caused by environmental change in one's home environment. Solastalgia, coined by the Australian philosopher Glenn Albrecht in 2003. It describes the grief and anxiety that comes from living through the transformation of a place you love. Watching the landscape that formed your sense of home and belonging change in ways that you did not choose and cannot reverse. Solastalgia is not the same as nostalgia, which is a longing for a past place you have left. It is a longing for a past version of the place you're still living in, a place that is changing around you. Research on solastalgia has found it to be prevalent among communities experiencing rapid environmental change. Ranching communities in the drought-stricken West, fishing communities watching salmon runs collapse, farming families dealing with increasing crop failures, residents of coastal communities watching their shorelines erode. The distress is not merely about economic loss, though economic loss is real and severe. It is about identity, the loss of a relationship with place and season that defined who these people are and how they understand their lives. The breakdown of the seasons is not just a technical problem with a technical solution. It is a transformation of the lived environment that is affecting the well-being, identity, and sense of meaning of people across the country. Quantifying this loss in the currency of economic impact, in the dollars of crop failures and infrastructure damage and healthcare costs, is necessary for policy, but it is insufficient for understanding the full scope of what is being lost. The temporal rhythm of the natural world is the framework within which human life has always been lived, and its disruption reaches into places that spreadsheets cannot capture. That noticing matters. It is the beginning of a reckoning with what is being lost and what must be done to prevent the worst of what is coming. The data confirms what people are feeling. The science explains the mechanisms. The policy question, what we do about it, is a question about what kind of future we want and what kind of risk we are willing to accept. The line between seasons broke down. It is breaking down faster. And the rate at which it continues to break down is still within human influence. That is not a consolation. It is a responsibility.